Okay, so now let's go ahead and take an example and let's walk through what the differences mean, right? So 7 volunteers taking the GRE allowed nurses to measure their pulse rate just prior to the start of the half-day test and at the end of the half-day test. Researchers wanted to determine if the heart rates of the students were greater prior to the test, prior to the start of the exam. The results are summarized below. So they have 7 volunteers. This is their pulse before taking the GRE and then after taking the GRE. So why are these match pair datas? Well, why are they match pair? Why are these samples dependent? Well, because the same subjects in the second sample is in the first sample, right? And so these are matched pairs because the subjects in the first sample are the subjects in the second sample. Now, now that we know that they're dependent in matched pairs, and one of the key things is that when you see two samples, but before and after, that's your red flag that that's going to be dependent. Right? Two samples before and after, that implies dependent match pairs, and then you're going to look at the differences. Now, I would keep it straight. Before is going to be list 1 or mu sub 1. List 2 is after mu sub 2. Keep it straight, right? Okay, so first of all, we need to make sure that the differences are normally distributed, right? And they come from independent sampling, right? So the only way to do that with small samples is the box plot and the normal probability plot. So let's go ahead and do that. So if we do the preliminary, that's essentially what we're doing in part B, is we're first testing, well, the number of people of your sample is 7, and is that less than or equal to or no more than 5% of all students taking the GRE. Right? And the answer was, yeah, 7. There's a lot of people taking graduate entrance exams, right? And so the second part with means is the sample size 7, is that greater than or equal to 30? And the answer is no. In fact, it's less than 30. But again, because we're given raw data, we can go ahead and do a box plot and a normal probability plot. And recall the box plot has to contain no outliers, and the normal probability plot has to show a pattern. And so let's go ahead and do that. Let's go ahead and put these two columns in list 1, list 2, and then do a list 3 for differences. So I would go to the calculator and go to stat and go to edit and put before in list 1 and after in list 2. So let's go ahead and put their pulse rates in. Okay, so here's list 1 is before, List 2 is after, but this is dependent sampling, so I gotta go to list 3 and put in the differences. And how we put in the differences is, don't go ahead and subtract in your head. Go ahead and up and highlight list 3 like mine is right here on the calculator. And keep it straight, keep list 1 minus list 2, before minus after. So hit second L1 minus second 2, which gives you L2, and hit enter, and then they'll all pop up. Isn't that cool? So we're going to use list 3 as the differences. So I'm going to drag this over. Okay, and then here is before, after, and the differences. Okay, so now let's go ahead and do that probability plot. The box plot. Yes. So now go to y equal, make sure there are no graphs in there, and let's go to second stat plot and hit 1. And make sure turn it on like it's highlighted on. And then let me go down and do the box plot with outliers. And I'm going to do it not on list 1 or list 2, but my differences. And I mark mine blue. Now remember, go to zoom, don't hit graph, go to zoom stat, right? Zoom 9, and it'll make it a nice little picture. We can see that there are no outliers here. And now let's go ahead now make that normal probability plot. So now go back to second y equals, which gives you the stat plot, go to 1, and everything's already in there, so I would just keep on plot 1 and then go to that normal probability plot, which is the last graph on that right side, hit enter. It'll still keep that list 3, and then now it marks it blue, and then perfect, hit zoom stat, zoom 9, and it gives me that normal plot. Okay, so now we have these pictures that we would have used prior anyways, right? So because we were given raw data with a sample size less than 30, then we can make a box plot and make sure there's no outliers. We did a box plot. And we can see that no outliers. And here we did a normal plot, a normal probability plot. We can see that there is a distinct pattern. As x's increase, we could see that these dots are also increasing, kind of making almost, you could see a line, right? A nice line. There's nothing out here, or dots aren't going zigzag anywhere. It seems like as it's going left to right, increasing left to right. And so therefore, there's a distinct pattern. And because these two are met, we can assume not the samples, right? The differences come from an approximate normal distribution. So we can assume the differences come from from normal population. So I just want to highlight the fact that we are not testing about the samples. We looked at the samples and they're dependent, and now we're looking at the differences. Okay. I think we're good to go. This was all preliminary, nothing we haven't seen before except the fact we were just doing it on the differences. So now let's go ahead and test it. We did it. This is the mind process. So I see that I have 2 samples. I see before and after. I know that it's a 2 sample with dependent sampling. I know I'm not going to do a 2 sample test. I'm going to calculate differences and do a 1 sample t-test. And I still have to meet the conditions in the preliminary criteria for the differences. Okay, so now let's go ahead and scroll down to the next page and go ahead and let's conduct a hypothesis to determine if the mean pulse rates of the students greater at the beginning. So maybe they were really nervous and had anxiety in the beginning, and then after it was done, they walked out, they were like, yay, I did it, it's done. So let's go ahead and start that 5-step process. So the first one is to identify the hypothesis. And we're going to have the mean difference status null. There is no difference between the heart rates. And then the difference here, and then this, we're going to have to do a little bit of side work here. Okay. So let's go ahead and take a look. If we're saying list 1 is before, list 2 is after, and if the student's heart rate is greater at the beginning than at the end, which is list 2. So then we're saying that mu sub 1 was greater at the beginning than the heart rates after, which is mu sub 2. Let's follow the pattern. I'm going to subtract mu sub 2 to the left and have mu sub 1 minus mu sub 2 greater than 0. So this is equivalent as when I did list 1 minus list 2 greater than 0. And list 3 is really just the differences greater than 0. So notice here that in this process, I realize that I have a right tail test. This is the claim. And I have the differences are greater than 0. The second part is to draw a figure. So we'll draw by calculator. The third part is to identify the alpha, which is 0.05, and then the step 4 would be p-value. The p-value approach, and again, what you're going to test on is you're going to do data, and you're going to pick, right, the differences. It's very important that we do that. And let's go to the calculator and see what that looks like. So here, I'm going to go to stat, and then I'm going to go to test, and I'm not going to go to a 2-sample t-test, right? Because I'm not testing about 2 samples that are independent. I'm doing 2 samples dependent, which turns into a 1-sample t-test on the differences. So go to 2, you have data, okay, and you're testing about 0 on the differences in list 3. Leave FREC 1, and you're doing a right tail test. Okay. And so let me go ahead and drag this over. Okay. And now I'll hit OK. And now I'll go ahead and hit draw. So it's drawing the normal curve, shading in that p-value. And don't mind the dots. Those are from the scatter plot so that we just did. So let me go ahead and put that in. So now, what does this mean, right? So here's the p-value, and now we can compare this p-value on the differences, 0.1407, on the alpha, 0.05. Okay, so 0.1407 compared to 0.05, this means that the p-value is um, larger than alpha. And what does that mean? Let's not forget, okay? This means that if I took another random sample of treatments with the heart, taking heart rates of students taking the GRE before and after and getting the same results as I did is highly likely. And that probability is higher than making a type 1 error. That means that most likely there's not going to be a change and there is no reason to reject the null, right? So here we're going to not reject the null. So if you do not reject the null, then you keep the null and you reject the alternative. And because the alternative was your claim, is there enough evidence to support your claim? No, right? And so therefore, there's not enough evidence to support the claim that the heart rates are higher at the beginning of the exam than at the end, right? So let's go ahead and interpret that and write that out. So in step 5, we can say that there is not enough evidence to support the claim that prior to the exam is greater than after the exam. And you can say that the pulse rate of an individual prior to the GRE exam is greater than after the, I mean, you could be more elaborate, but I think this is good. It shows that you understand how to interpret in terms of the claim and in context of the problem. So if you want to go into further detail, you're more than welcome to do that.